Today we're going to be talking about applications of differential equations, and a specific example of that is exponential growth and decay. So you've been dealing with exponential functions since you were in Algebra 1. Now we're going to look at it from a calculus perspective. So exponential growth and decay occurs when the rate of change of the quantity is proportional to the size of the quantity, resulting in the differential equation dy dt equals ky. So the rate is directly proportional to whatever the size is. So we're going to solve this differential equation by separating our variables. Okay, once we have them separated, we can integrate. So this is going to be the natural log of y equals kt plus c. I want to solve for y, so we'll raise both sides to e. So we're going to have e to the kt plus c. And we can rewrite this as e to the kt, e to the c, which we now know we can write as ce to the kt. If you have an initial condition, where at 0 you have some amount. So let's plug that information here. So I'm saying when time is 0, we have an initial amount. Well, this is just going to be 1, so C is going to equal that initial amount. So our general solution is going to be y equals y naught e to the kt. So this is something you're just going to want to know, that if this is the differential equation, that its general solution is always going to be this exponential function. All right, so now we're just going to look at some different scenarios. You run over a nail. As air leaks out of your tire, the rate of change of air pressure, P, inside the tire is directly proportional to that pressure. Write the differential equation that models P as a time of t. So this is very, very common for these types of questions. They're going to say the rate of change is proportional to the quantity, which means that dy, or dp this case, dt is going to equal k times whatever the pressure is. The general case, P is going to equal the original amount, E to the kt. Okay, so now let's get some numbers involved here. It says find the particular solution when the initial condition T0 is 35 and 7 minutes later the pressure was 33. So 33 is going to equal the initial 35 e to the k times 7. Now we're going to solve this for k. So we'll divide, take the natural log, gives us 7k. So that means our k is going to be the natural log 33 over 35 over 7. Now you're going to want to maintain calculator accuracy. So to do that, you either need to just leave it like this or use a lot of decimal places. Just for the sake of ease right now, I'm just going to go ahead and use the decimal places. So 0.00084. The more you use, the more accurate you're going to be, and this will be fine for us for right now. So now my general solution, P, is going to equal 35e to the negative 0.0084t. Okay, so now we're going to use that equation. So what will the pressure be 10 minutes after? So that's just simply plugging in 10. Which, type that all in your calculator, we're going to get 32 0.180 psi, always 3 decimals unless you're told otherwise. Says the car is safe to drive as long as the pressure is 12 psi or greater. So how long after the puncture will you be able to drive the car? Now realistically, 12 seems a bit low in my opinion, but we'll go with it. Okay, and this is just an exponential equation that you've been solving really since Algebra 2. So we're going to divide take the natural log, okay, and then our last step is to divide. So our t is going to be natural log 12 over 35 all over negative 0.0084, which gives us a time of 127.433, and our time units were in minutes. So you got about 2 hours till you're in trouble. Okay, population growth is another one. So the rate of growth of a population is proportional to the size of the population at any instant. If the world population was approximately 6 billion in 2000 and approximately 7 billion in 2010, we're going to write a differential equation that's going to model this. So just d, we'll use p for population, over dt is k times p. The general solution then, p, is going to equal p naught e to the kt. Now we're going to find the particular solution, and we're just going to say 0 is that 6 billion, so 2000 is going to be times 0, so in 10 years we'll have 7 billion. And again, solve this. So we're going to divide by 7, or divide by 6, take the natural log, and divide by 10. Gives us a k value, and I'll just leave it like that because these numbers aren't bad. So my general thing, and again, you can use a lot of decimals to overcome that. So my k is going to be the natural log of 7 over 6 over 10 times t. So estimate the population at the beginning of 2025. We're just going to plug in 25. And let the good old calculator give us 8.821 billion. Okay, and then when will the population double? So if it's 6 billion in 2000, we're looking for it to equal 12. And we're solving for t. So we'll divide by 2. And this is always going to be the case in these situations. If we're looking at doubling time, this is always going to be 2. So then I'm going to take the natural log and then divide by that. So we're going to have the natural log of 2 divided by the rate. So this is always how you find doubling time. Calculator gives us 44.96, which is pretty close to 45, but not quite. So I'm going to say in 2044, it'll be late in 2044, but it's going to tick over sometime in that point, according to our model. Okay. Bacteria in a certain culture increases at a rate proportional to the number present. If the number of bacteria doubles in 3 hours, how many hours will it take for the number to triple? All right, so if it's directly proportional, that means dt is equal to kb, which means our general solution e to the kt. Okay, well, just like the last one, if I'm looking for the doubling time, then that means if I divide this by this, I'm going to get 2. So we're saying 2e to the k times 3, because it took 3 hours to double. So I'm going to take the natural log of both sides and divide by 3. So that's my k. Now we're looking for how long it takes to triple. So 3 is going to equal our k is now ln 2 over 3t. And we're going to solve. We'll take the natural log of both sides. And solving for t, I'm going to multiply by the reciprocal here. So we're going to have 3 ln 3 over ln 2 is our time, which is A. Okay, our next example, a colony of bacteria grows under ideal conditions so that the population increases exponentially with time. After 2 hours, there are 500 bacteria. After 6 hours, there are 10,000 bacteria. How many bacteria were there initially? Okay, so we're working backwards. We know hours, we have 500. We know in 6 hours, we have 10,000. We're trying to backtrack here. So what I'm going to do right now is just pretend that 2 is my initial one to get my k value. So I'm going to set 10,000 equal to 500 e. We're going to find our k. The time it takes to go from 500 to 10,000 is going to be 4. So we're going to take the natural log and then divide by 4, gives us our k. So now to figure out the initial amount, I'm going to use either one of the things. I'm just going to use the 500. So I'm going to say 500 equals the initial amount that I don't know, e to the natural log of 20 over 4. The time it takes to go from 0 to 500 is 2. So our initial amount is going to be 500 divided by this whole thing, e to the natural log 20 over 4 times 2, which gives us 111.803 as our initial amount. Okay, rate at which a certain radioactive element decays is proportional to the amount present according to the equation dy dt equals negative 1.2y, where t is measured in years. What is the half-life of the element? Okay, well, if this is our equation, then the general solution is going to be y equals whatever the original amount is, e to the negative 1.2 t. And you could solve this a long way if you don't remember the general solution, but anytime you have some constant, anytime it's this setup, it's always exponential. So if I'm looking for the half-life, we're looking for this to become half. Okay, and we'll just solve this. So natural log of 1/2 is going to equal negative 1.2 t. T is going to equal the natural log of 1/2 over negative 1.2, which is approximately 0.576 years. Newton's law of cooling assumes the temperature T of a small hot object placed in a surrounding cooling medium of constant temperature Ts decreases at a rate of T minus Ts. So the difference between the temperatures. So as the temperatures get closer, the rate is less. Okay, so an object is cooled from 100 degrees to 40 degrees in 20 minutes when the surrounding temperature was 20 degrees. How long did it take for the temperature to reach 60 degrees on the way down? Right, So let's start with the differential equation. Okay, this says that the temperature is directly proportional to T minus the surrounding temperature, which for our problem is 20. Okay, we'll go ahead and solve this differential equation. So dt over T minus 20 is going to equal K dt. So the natural log of T minus 20 is equal to KT plus C. So T minus 20 is going to equal CE to the KT, and then we're going to add 20. So our temperature is CE to the KT plus 20. And you may remember this formula from pre-calculus. 20 was that surrounding temperature, but we arrived at that through calculus. All right, so now what I want to do is find my value of C. Okay, we know that its initial temperature was 100. So 100 is going to equal CE to the 0 plus 20. So my C is going to be 80. So my now equation is T equals 80 e to the KT plus 20. Next thing we need to find is K. And we're going to use the fact that it went from 100 to 40 in 20 minutes. And solve this. So I'm going to subtract 20 from 40. Divide by 8, which is going to give me 2/8 or 1/4 if you want to reduce it. And we're going to take the natural log and then divide. So K is the natural log of 2 over 8 over 20. Now we have our K. We're going to figure out the time it takes to get 60. So we're solving this equation, so I'm going to subtract 20 and then divide, so that's going to give me 40. 40 over 80 is going to be 1/2. Take the natural log of both sides, which is going to give me this, so then I'd end up dividing. But do it 2 over 8 over 10 times t. So my t is the natural log of 1/2 divided by that whole mess. Okay, which is 10 minutes. All right, here's another example of applying differential equations. So a new dam is constructed across Scorpion Gulch. Engineers want to predict the amount of water in the lake behind the dam as a function of time. At t equals 0 days, the water starts flowing in at a fixed rate F, cubic feet per hour. Unfortunately, as the water level rises, some leaks out. The leakage rate L is directly proportional to the amount of water W in the lake. Thus, the instantaneous rate of change of W is F minus L. So what is L equal in terms of W? It says L is directly proportional to the amount of water W. So L equals KW. And it says write a differential equation dW dt in terms of F, W, and T. Well, this statement, the instantaneous rate of change of W is F minus L. So dW dt is equal to F minus L. Well, we said L is KW. So this is going to be F minus KW. It says water is known to be flowing in at 5,000 cubic feet per hour. Based on geological considerations, the proportionality of the constant is equal to 0.404, so we don't have to solve for that. Also, when t equals 0, w equals 0. Write the equation for w, substituting in these quantities. Okay, in my notes online, I solved this differential equation generically, then plugged in the information. Here in the video, I'll do it the other way around. So dw dt is going to be, F we know is 5,000, minus the K they tell us is 0.04 times W. All right, we're going to separate the variables. So we're going to have dW over all of this, 5,000 minus 0.04 W equals dt. Then we're going to integrate. So this is going to be the natural log of 5,000 minus 0.04 W. But then we have this. If I were to take the derivative, we'd multiply by negative 0.04. So here I'm going to divide by that, equals T plus C. Okay, so I'm going to multiply over we'll multiply over negative 0.14, so ln 5,000 minus 0.04 W equals negative 0.404 T plus C, because if I multiply the C, it doesn't matter. So we'll raise both sides to E, so 5,000 minus 0.04 W is going to equal CE to the negative 0.04 T. Okay, I'm going to move up here. I'm going to subtract 5,000. Before I do the next step, I'm going to go ahead and solve for my C. So we know T is W when T is 0, W is 0. So when this is 0, CE to the 0 minus 500. So that means our C is going to be 500. Sorry, 5,000. E to the negative 0.04 T. Then I'm going to divide by this negative 0.04, which gives me a negative 125,000 E to the negative 0.04 T. Minus 5,000. Keep dropping things. Okay, so we got this whole big thing. To make it a little bit simpler, I'm just going to factor out a 125,000, which would leave me with 1 here and just this. So I'm going to have 1 minus E to the negative 0.04 T. So when will it have 100,000? We'll just solve that algebraically. So I'm going to divide. Subtract 1. Make it the opposite, so this will now be 1 minus 100. Okay, and then we'll take the natural log and divide by that. So we're going to have the natural log of 1 minus 100 over 125 is equal to t. Calculator will give us 40.236, and this is in hours. Okay, the rate at which a baby bird gains weight is proportional to the difference between its adult weight and its current weight. At time t equals 0, the bird is first weighted. Its weight is 20 grams. If b of t is the weight of the bird in grams at any time t after its days before it's waived, then db dt is 1/5 100 minus b. Okay. Let y equal b of t be the solution to the differential equation with the initial condition that b of 0 is 20. Okay. Is the bird gaining weight faster when it weighs 40 or when it is 70? So we're simply going to plug in the b, 40 and 20, to see which of the rates is bigger. So we're going to plug in 40. So I have 1/5 of 60, which gives us 12. And then if we evaluate this at 70, that's going to be 1/5 of 30, which is 6. Okay, so the bigger one is 40. So it's growing faster at W equals 40. Which makes sense. You grow fast initially and then it slows off. Write an equation of the tangent line to the graph of b at t equals 0. Use this equation to estimate the amount the baby weighs after t equals 5. All right. So at t equals 0, db dt is 1/5 of 100 minus 20, because that's the weight at 0. So this is going to be 16. So that's going to be my slope. Okay, so I just plug in my initial value, 0 and 20, and then my slope is 16. So this is 16t plus 20. And then if we want to use that to predict at 5, we'll just plug in 5, which of course on the AP exam, that is a legitimate answer to this question. I'll go ahead and take it a step further. You know, if you have a calculator, you might want to use it, but really it's probably just good policy to leave it like that and avoid any potential errors. Okay, now we're going to take dB, the second derivative. Okay, so when we take the second derivative, okay, this is really going to be 100 over 5 minus 1/5 b. So if I take the second derivative here, so it's going to be the derivative of negative 1/5 b, but then we have to do this, the chain rule, and the derivative of b with respect to t is dB dt. Okay, so the chain rule never goes away. So now this is going to be one-fifth of 1/5, 100 minus b. Go ahead and simplify that a little bit. Okay, and then it says use this to figure out if our tangent line approximation was an overestimate or an underestimate. Well, if I plug in a weight less than 100, then this is going to be positive, which makes the whole thing negative. So if our second derivative is less than 0, we are concave down. And if we have a concave down graph with a tangent line, our tangent line is going to be an overestimate. Okay, it says use the second derivative to explain why this cannot be the graph. Well, if it's always concave down, then this can't be the graph because that's clearly concave up. So just something like that. Graph is not always concave down, but it should because the second derivative is less than 0. All right, we've been dealing with the differential equation. Now we're actually going to solve this guy. So separate our variables. And we will integrate. So this one's going to be the natural log of 100 minus b, but because that's negative, using the chain rule, we need a negative, is going to be 1/5 t. Okay, raise both sides to the e, so 100 minus b is going to equal c e to the negative 1/5 t. I'm going to solve for my initial condition here, and you can solve at any point, just kind of when it looks convenient. So if I plug in, my weight is 20, so 100 minus 20 is going to equal c e to the 0. So my c is going to be 80. And again, you can do that at any point where you feel like it. So we'll subtract 100. And then multiply by -1. So b is going to be 100 minus 80 e to the negative 1/5 t. So that was an actual AP question involving differential equations and their application.